like Arun said, SLAC is the national lab. How many of you actually ever heard of SLAC before? Oh, wow. That's amazing. So I've been here 5 years. Okay. I've been coming down to campus to talk to faculties, to introduce myself, introduce SLAC. Most of the time, I get a blank stare at me. Says, "What is SLAC?" And so this is a very good start. The other thing Arun said, SLAC is a very different place, and so I'll tell you a little bit about it. I also trained as a chemical engineer. It's a very unusual for SLAC. SLAC was a high energy physics lab. So when they realized a chemical engineer now became the lab director, people were freaking out. So for me, energy was always part of the thinking. And at the graduate school I went in there, my thesis advisor says, if you have a solution to turn sea water into an ice cube this big, you don't need to write a thesis. If you can't have a way to do that, you have to write a thesis. So it took me 5 years to write a thesis because I didn't have an answer for that. So maybe some of you have the answer for that. So coming back to what Arun says, national labs. There are 17 of labs like SLAC. There are 10 of them belongs to the Office of Science. Office of Science funds most of the physical science in the United States. So the budget for Office of Science is $5 billion a year. And about 60% of the budget for Office of Science is supporting large user facilities. Facilities that university and company simply cannot build and operate by themselves. So SLAC is one of those 10. The history of the lab, if you look at it, the signature piece, if you drive up Sand Hill Road, is labs on your left-hand side, 2 miles up, or you drive around 280, you will see it too. The signature piece is the 2-mile LINAC. That was built in the 60s. A few faculties at Stanford decided they want to build a highest energy electron accelerator at the time, so they can understand the structure inside the nucleus, the quarks, essentially. So with that LINAC in the 70s and 80s, there were a series of work done, and that led to 3 Nobel Prize SLAC. And then we got into the X-ray game. So today we operate 2 X-ray facilities. The first one is a little storage ring called Stanford Synchrotron Radiation Light Source, SSRL, which I will talk to you a little bit more about it. I think maybe a lot of you eventually will get to use the facility as well. And so that is a facility. Bert Richter discovered a J-site particle in the 70s. He built that, basically used the discretion to fund the laboratory. That was the good old days where laboratory has complete control of the budget at the time. So then what happened was, as Bert doing his experiment, 2 faculties, one in applied physics and one in material science, went to Bert and says, can we actually open up the vacuum chamber, take X-ray out? So people at the time were thinking, maybe this is a way you can actually produce an X-ray source, which is a lot more powerful than the X-ray source that you have in the lab. And so Bert, being very nice, and said, fine. So they built the first sets of instruments at SSRL. That was in the 74. So, and then evolved, eventually Department of Energy took offer and operate as a national user facilities. So I'll talk to you a little bit more about that later. The next machine is the linear coherent light source. So this is an idea that started at Stanford in the 70s. A faculty by the name of John Mady. John came out with the idea to produce a laser that cannot be covered by the typical crystals that you can use generate in the different frequencies. And so he came up with the idea in the infrared. So in the 80s, people started to think about, can we extrapolate that from infrared to X-rays? That's a huge leap. Infrared free electron lasers fit about the size of the platform here. For X-ray, you would need a 10 GeV of electron beam. You would need a very long magnetic structure to generate the X-rays and all that. So people thought that was almost impossible to do in the early 80s. But then came Reagan Star Wars time. People are talking about maybe building a machine like that for missile defense. And so a lot of technology were developed in industry and also in the defense labs and also elsewhere. So by the 90s became clear we had all the pieces that we need, although still risky to put everything all together and expect that to work. And so SLAC at that point realized the highest energy, high energy physics accelerator now had moved on to CERN. Like you probably heard the discovery of the Higgs boson at CERN a year ago. So it was clear the laboratory needs to transform itself. So lab then took on the idea of building a free electron laser, utilized the lignite that we had. And so that led to the second X-ray facility at SLAC. So the next few slides, I'll show you what we do with them. So SSRL. So the way it works is you have electrons. If you have a magnet, you would bend the electron around an orbit. As the electron accelerates around the orbit, it radiates. So the radiation depends on the wavelengths of radiation or energy depends on the energy of the electron beam and the strength of the magnetic field. So now if you do that, you can make a circle, right? So at any given time, there are 30 instruments at SSRL that people can do experiment with. Because the energy and also the current that we have in the storage ring, the intensity of the X-ray you get out of this compared to the X-ray machine that you typically have in the lab, like some lab here in McCullough, is about 1 million times more. 1 million times more in intensity compared to the X-ray labs that you have in your lab or in elsewhere. So people can do all kinds of stuff with it. And so for SSL at the moment, the emphasis actually is to understand how materials work. How do you process it? How do you understand the performance of it? And so this is a machine you can get time on if you write a proposal. It's completely free. So anybody who has a good idea can write a proposal. And once you get approved, the facility will help you allocating time, and the staff will help you do the experiment. So I think a lot of Stanford students actually working their thesis at SSRL. I think every year they have about 40, 50 PhD theses done at SSRL. And so just give you 2 examples of what kind of things people do. If you have a lot of X-rays, one thing you could do is quickly looking at things, right? So you probably heard about material genome. It's an initiative launched by White House a few years ago. The idea is that the computing power today are so much better than before now. So you don't have to do a lot of trial and error. If you want to find a new materials for batteries, for alloys, for whatever application you might have, you can do is to do a lot of computation first. You find out roughly where you want to look. And then you go try to make materials that you want. Right? So that narrowed down the search tremendously. What SSRL and a facility like that can help you, the next step is actually, because the intensity of X-ray is so strong, you can go through thousands of samples every day. Right, so this is one example. People looking for a new magnet because the critical material, we don't have some of the rare earths that we need for making strong magnets, which is very important part for cars. So looking for a new composition. So the way they do it, they have a wafer, and they have they deposit different elements into it. So essentially, one wafer, you have the phase diagram of the alloy, right? So they make this, they ship to SSRL, and you can go through them quickly. So the next step, what you like to do then is to be able to measure the property at the same time you're doing the measurement. Right? So that's the next step we do. The other thing that you can do when you have a lot of X-ray, the X-ray is very bright source, is you can do more imaging. You can get to much higher spatial resolution. So in this case, you look on the upper right-hand side, it's a typical microscope. You have an objective, except in this case, it's X-ray lens. Right? It took people many years to develop an X-ray lens, so we now have it. So this instrument can give you 30 nanometer resolution in 3D and with the chemical sensitivity. So once you have a material, you want to understand what's inside, you can treat it with high temperature, pressure, and whatever you want, because X-ray can penetrate through all these environments. Right? So the emphasis now for SSRL right now on the energy side is to make these tools available to people who want to develop new materials, understanding the property of those materials. So there's a lot of work between Stanford faculties and SLAC happening now. So next thing we're doing now is actually working with industry, try to bring this all together so that what we do is more relevant. So next 2 slides, I'll show you about the LCLS, the free electron laser. So one technical slide. So the storage ring is electron are going through a magnetic structure. So the green and gray part are up and down, north and south. As electron going through, it gets wiggled. Every time it gets wiggled, it emits X-rays. But the way they do it is independently. So every electron emits by itself. So you add intensity. In the free electron laser case, it's actually the radiation feed back to the electron beam itself. So the X-ray generated by the electron beam actually interacting with the electron beam itself, because X-ray has electric field, magnetic field. Right? Essentially, you use the X-ray itself to interacting with the electron beam. So the electron beam then structured. So eventually, the structure of the electron beam, it radiates. So now all the electrons radiate at the same time in amplitude. So there are 10 to the 9 electrons in a bunch. So if you measure the intensity, then it's a 10 to the 9 square. So compared to synchrotrons, the free electron laser gives you 1 billion times more peak power. Okay, so this is amazing new source that we have now. The things you put in front of it vaporizes if you focus the X-ray beam down to it. But the things are moving so quickly, the X-ray bunch is so small, you actually get information you want before there's a chance for atom to move away. So I'll give you the example later on. So this was sort of a science fiction in the 80s. By 2000 time frame, people said, okay, maybe this was well to invest. So Department of Energy gives SLAC $400 million to do this. And we built the undulator, which is the magnetic structure you see in the cartoon there. That thing is 100 meters long. You have to align the pieces of magnet to micron precision for this to work. Okay, so laboratory has hundreds of professionals. This is what we do. And then, sure enough, this is what we get. If you look at the electron bunch, this is actually the structure of the X-ray coming out of the structure from the electron beam. We now can measure it, so we know the X-ray pulse only coming on 10 femtosecond duration. Okay. 10 femtosecond, that light only go about this far. Right? So this is a real feat. This machine came online 5 years ago. So let me give you a few examples what people are using it for now. So remember, a lot of things you probably will hear either this morning or the rest of the week is try to understand chemical reactions. In this case, it's a CO oxidation by oxygen on the surface of metal. With LCLS, we can actually now start a reaction and follow it femtosecond at a time. You can make a movie out of this, right, which is something we've never been able to do before. Right, so this is actually a real example. I mean, this is a science paper came out a year ago. And the bottom piece is another one. So a lot of the protein structure people are interested in get damaged if you expose it to X-ray for too long. But like I said, because this pulse is so short, there's not enough time for atom to move. So we demonstrate this by showing you at 0 femtosecond there's image, at 100 femtosecond there's a second one. You can see the density map actually changed a little bit. So one of the disulfide bond actually broke between the 0 and the 100 femtosecond. You see the bond actually move. Okay, so this is the first time you can get insight of how these things work now. Okay. The last piece on top is superconductivity. There's a lattice distortion once you quench superconductivity. So this experiment requires very, very high magnetic field. So this is done at 30 Tesla. So the only way you can do it is it has lots of X-rays in very short time. So this is a very important experiment as well. So these are the two facilities I described to you, the storage ring and also the new facility, the free electron laser. If you do research on materials, if you understand processes, these are the tools, are fantastic tools for you. Now, the lab has changed quite a bit. So I came here 5 years ago. I became the lab director 3 years ago. And so we looked at what we have. So if you look at the right-hand side, it's the big facilities, which we have the two best facilities in the world, and uniquely you have two facilities in one place. So we're doing now then is working with campus faculties and students to do the best science that can use the facility. This facility, somebody need to understand what's the best use of them, right? So we do a lot of that now. And the third piece is actually the reason why we're here, because Department of Energy, I think Arun knows very well, looking at says, okay, the department has $27 billion a year budget. What have we done? Can we actually speed up the discovery of materials so that we can actually make real impact to society? Now you say, where can this happen the most efficiently? I guess MIT and Stanford, probably, right? In terms of people knows the real world and can bring the fundamental discovery to real world. I think these are probably the two best places. So then, since SLAC is right next door, so the question is, can a laboratory help more by working with campus more? Right? So facility is only part of it, and we can do more. Last piece is the high energy physics tradition of a lab. Now we have turned all the instrumentation scale that we have. Now building detectors for cosmology. So we have a satellite now in space looking at gamma rays. We just start to build a optical telescope on the mountain of Chile, which will scan the southern hemisphere of the sky every 3 days. Okay, so there will be petabytes of data coming out of the telescope that we expect discovery from that. So let me tell you what we intend to do going forward then. There are 3 joint institutes. Stanford has 18 of them. I think 3 of them actually are joined with SLAC. So we'll continue to build on that so that the institute, like SIMES, I think is heavily involved here. It's a way for the laboratory to involve more faculty and students with labs. A second thing we're doing now is we try to teach more. So because we provide unique tools, so but if you don't know about how to use the tools, you won't be able to use it, right? So we encourage the SLAC faculties to teach more on campus, so that you can be better informed about what can the tool do for you. And we also try to create more research opportunity for students, because ultimately we want to hire the best people, and then hopefully some of you will end up in the lab. Then the third thing actually is the way we actually grow the lab. The lab has a budget about $300 million a year operating, and another $200 million a year that we use to build new facilities. So what we are doing now is actually working with Arun and people, is to bring faculties into the lab and have them map onto the mission needs of the Department of Energy. So then it's a win-win for everyone, right? Because the Department of Energy now get to have the best faculty to work on the problem they care about. And through the lab, and in the lab we have is the facilities. Now the facilities are used to work on problems the department cares about also, right? And in order to make all this fit, then we are building a new lab. So that's a 100,000 square feet lab at SLAC. It's a jointly funded by Stanford and Department of Energy. It will come online 2018, so 2 more years. So some of you probably may get to use it. So we're in the process now planning allocation of the space, and also what instrument we want to put into the lab, so that they complement all the instrument and the lab that you have here. Lastly, I want to close this now. It's come up to SLAC sometime. If you drive out Sand Hill Road, you won't miss it. You will see the signature building on your left-hand side, the red roof. And so this will be completed in a month's time. Hopefully you will have time to come up and visit us. Thank you.
We have time for a few questions.
I was just wondering, is there a procedure for private companies to get beam time at SLAC, and has anybody ever done that?
Good question. Yes, if a company doing works that they intend to publish, they apply for beam time just like everybody else. If they intend to do proprietary work, which means they don't want anybody knows what's in the sample, they have to pay for what we call the full cost recovery. So the way we do it is we take the operating funding for the facility, divide by the number of instruments, divide by the hours. So for SSL, I think that's about $1,000-ish for 8-hour shifts. And we have about 1% of the revenue actually coming from that. For us, we not really want to make money. We really want to is work with them, have impact, right? So the way it works actually very nicely now is the faculties working with SLAC staff, developing the tools industry may want. So once the faculty's done it through working as students, you publish, right? And there's this industrial affiliates program here, so that they can talk to the industry. So industry know the capabilities is there, and also they have people to help them. The industry then come to use the capability. So I think that's probably the best way. We have not done a lot. I think this is something we'd like to do more. Any other questions? Okay.